putting them together. This is the base for every analog electronic device that we deal with nowadays. Since the invention of PN junction, you have diodes, transistors, and there are infinite varieties of diodes and transistors are available, right? So when we put them together, what will happen? At the instance, you are forming a junction. Junction is basically a location where two materials are meeting, right? Or two or more. For example, in electric circuits, also we have a junction, correct? So where everything is meeting at one point. So when you take a piece of silicon, from one side you dope with trivalent. Remember, trivalent means it gives you p-type. From one side you dope with pentavalent, which will gives you an n-type. So right at that point, a boundary will form called as a p-n junction. So it's a junction formed between p-type or p region to the n region. You can look here on the p region. What is majority here? Positively charged. So you see there are lot holes compared to the electrons. Electrons are 6 or 7 in here, right? There are only 7 electrons, but the holes are very high or very rich. But oppositely on the n-type n region, you see electrons are dominating, but there are only like 3 holes right there. Right? And this p-n junction, when you have something like this is the base for, so if you have one p-n junction, 2 p-n junctions, it doesn't matter. P-n junction always behaves as a p-n junction. But depends on how many you have, in what order you have various devices, such as diodes, transistors. You have solar cells for converting light energy into the electrical energy. So all those are the basis for all of those is a p-n junction. So what will happen when I do this? When I put p-type and n-type together, what will happen is the discussion for the p-n junction. So when you initially form a p-n junction, like at the moment that you put it together, you see this line is very thin, correct? So the separation between these two is like a very thin junction. But as you wait for a few seconds, microseconds, this junction width actually increases, and it will be something like that. So you see that width of the junction is actually increasing, right? So why it is increasing? So why the width between the separation? So what will happen is, remember that you have an opposite charged particles on either side, correct? So now you are putting them together. So now what will happen is, for example, the electrons near to the junction will try to attract and try to fill to the holes on the opposite side, correct? So now there is a movement of these electrons will occur. So the electrons on close to the junction will try to reach to the other side, because there is a force of attraction, correct? So as they move, then what they will be leaving on the holes they will be leaving, right? So for example, if I have one electron that is moving, so let's talk about just one electron, then it's going to leave a hole behind. So for example, if this electron jumps and occupy that site, then I'm leaving a hole behind, but that electron will be here. Similarly, depending upon the number of electrons available on either on this side of the border, all these electrons will try to fill the position of the hole on the other side. Again, this whole things will happen because there is a force of attraction between the opposite charge carriers, right? Under the influence of the heat energy, they will move. Same thing goes. These electrons on this side will also, even though these are very small in number, they will also try to move to the other side if they are close enough to the border, right? So when a p-n junction is formed, some of the free electrons in the n region will try to cross the region or cross the p-n junction and attracts towards the holes. And the term used in here is diffuse. Diffusion is a term used if something is happening, like in this case, the electrons are moving under the influence of heat energy, correct? So they are basically being attracted towards the positive holes on the other region. So these electrons are diffusing by leaving behind, as you can see here, as this happens, on the n region, you have positively charged on one side of the region, correct? Because as the electron moves, you already have by default a positively charged ion on the other side. Same thing goes on this side. Because when that electron comes here, this will be electron. Same thing, then all these will be electrons if you think of, correct? If they're close enough to the barrier, then the other side will be positively charged. But how long this will happen? Does all of these electrons will get attracted to all of the holes in here? What do you think? So initially the electrons closer to the junction will try to attract, but as they're attracting, what will happen is you will creating a positively charged right here, and you're creating a negatively charged. What that charge will does is it separates the barrier. It makes the barrier wider. If you remember by definition of voltage, what is voltage? Voltage is not moving electron. Movement of electrons is current. Voltage is if you have two different types of charges separated by a distance, you have a voltage. Remember, voltage is also called as a potential difference, correct? If you have completely positive charge on one side, completely negative charge on the other side, and they are separated by distance, then you will form a voltage source. So what will happen is, once you place these two electrons and holes together, or sorry, the p-n junction together, you are actually forming one side completely positive, one side completely negative.
Why does not the next row?
There may be a possibility. Yeah, there may be a possibility. So I'm going to talk about that, because now you have this barrier. Let's say, for example, you have this little bit of barrier, right? This barrier may increases or decreases under the influence of the temperature. Because if this electron, let's say, for example, I have this barrier. If this electron has enough energy, it can cross the barrier, of course. Then what will happen? Then this barrier eventually will widens, correct?
Yeah, it seems like now that you got all those positive ones right next to your electrons on the inside, seems like they just go to those right into the barrier.
There is a possibility it can, if these electrons have enough energy, so that they can push through the barrier.
Now that these have all become positive, why does not this go there?
Okay, you have a separate, remember this is the absence of, this is only an ion. That means once the charge become neutral, there is not going to be anything available, is it? Remember, the neutral means the recombination. Once the electron gets into the hole, then what is the total charge? The charge would become a neutral, isn't it? Because electron and hole are equal in value, but they are opposite. Correct? So the charge becomes a neutral. This is an indication for neutral charge. Right. Can you wake him up? I think he became neutral. I think you might want to stand. I think it's better if you stand up a little bit. Or maybe wash your face. So that's the reason why, because these charges are already depleted to the other side. And they are already becoming neutral. So for example, I think it's easier to actually see. So let's say let's say this side is all positive. For example, I'm going to just ignore the holes, or sorry, the electrons on this side, but they will be available, of course. So on the other side, we have all negative, for example. So now if I have the electrons closer to the barrier, let's say this goes here, right? So what will happen is now you have the recombination. So that means the charge becomes neutral. Yeah. So now same thing, if this goes here, that becomes neutral. So now what is happening is the distance of separation to cause for further electron flow. Now there is nothing in here. So the electrons, if this has enough energy, yeah, hopefully it can jump to, it can recombine. Yes, at some point. It is possible. I will come back to that point shortly, and to your point as well, on how we can have further more. So let me delete few more of this. Now, for example, let's say they are all recombining. Again, everything is happening under the influence of room temperature. Again, we are not applying any voltage yet. Because of the nature of these particles, they are positive and negative, they are attracting to each other. So what happens in between is, again, so this distance, is there any charges in here? No, that's why the region is called as depletion region. Depletion means there is nothing going to be available in that region. But if I want to still move them, right? For example, okay, I want to still move this electron across the barrier, across the depletion region. If that electron has enough energy, it will do by itself. But if it does not have enough energy, because at some point they will stop moving. But if you want to further move it, then you need to apply the external energy to move them. But they will stop at some point. You have a question? Again, magnetism, you have the magnetic fields. They may or may not have, they don't have a magnetic field. It's a purely electric field. Yeah. So that region was depleted, meaning that nothing in there. That's why the name depletion region. There are no charge carriers that are available. So this depletion region can grow wider if the electrons have enough energy. But usually it will stop at approximately reaching 0.7 volts if it is a silicon-based PN junction. So how much that voltage worth? Because here you have completely positive, completely negative depletion on either side. So one side becomes hugely positive, another side becomes hugely negative. So the voltage that is worth of the depletion region is approximately, say, equal to 0.7. Again, when you test in the lab, you're not going to read 0.7. This is a theoretical value that we use for mathematical analysis. Everyone will read different. Someone will read 0.65. What does that mean is, this barrier potential is worth of 0.7 volts. So how much voltage should I need if I still want to move these electrons? I need more than 0.7, because if I apply 0.7, that will only counteract with whatever the 0.7 generated by the barrier. But if I apply more than 0.7, then I can have the further electron transfer.
Doesn't it add to the length of the barrier, or make the barrier?
This is only by default. Again, as I said, that value may change. For example, if you touch the PN junction with your fingers, that means you're raising the temperature. Correct? If you're raising it, then this voltage will go down. That means you need a less voltage to overcome the barrier.
We haven't talked about heat and light changing things. What about static electricity?
They may not damage, that's only a little bit, but they may damage some ICs. These won't get affected by the static a lot. But static is usually affected with a little bit more sensitive devices. ICs can be more effective with the static electric field. Unless, like usually some circuits has an ES, electrostatic discharge terminals. So we can discharge, or some bands that you can wear them. But in terms of that's not going to accumulate to this 0.7.
And even if they do with a higher voltage, if you transfer from one side to the other, nothing ever stays on constantly. When it goes off, it goes back. So if the barrier region can grow, can it also shrink?
Possibility, yes.
How does it shrink?
Yeah, we will talk about in the diode in the forward bias. There is a topic for it. So there may be, it shrink a little bit, not to an extent where this goes to zero. No.
Because if you had like 10 volts to it, wouldn't that just make
Yeah.
the whole thing neutral?
It may not shrink all the way to 0 volts, as I said. So you initially starting ideally at 0.7. But if you apply a little bit higher voltage, let's say you apply like 20 volts, which is way higher than 0.7, correct? It will increase the force for these electrons to push through the barrier, but depletion region may shrink a little bit only. So we will come back to that point when we talk about diodes. So under what condition it may shrink, but not to an extent where this becomes zero, no. It won't shrink all the way to zero. So I will come back to that point in the forward bias condition. So there is a condition for diodes known as forward bias. So under that condition, it may shrink a little bit.
So if you add too much,
Then you can damage the diode.
it could ruin the PN junction?
Yes. If you apply extremely high voltage, then it will damage. Again, there are some limitation to how much it can handle. Because if you apply too much voltage, the amount of current through the junction increases. So eventually the heat increases. That may damage the diode. But some diodes can handle 50 volts. The one in our power supplies, like chargers and batteries, the chargers, they have 400 volts. So it has a capability to handle 400 volts without breaking them. But there is always some value. And we will discuss that as well, which is called as a PIV rating of the diodes. But there is always a way, if you apply too much, you will damage. It's the same as any component for that matter, right? So again, the formation of the depletion region is showed here too, same explanation. In P-type, there are holes from acceptor impurities, which is your trivalent. N-type is a pentavalent. which has extra electrons. When p-n junction is formed, some of the electrons from n region will reach to the conduction band. Again, remember that conduction band is free and free to diffuse across the junction, which is shown in here. Leaves behind positive ion. Again, ion is a term that we use that basically shows that gap where the depletion occurs. So filling the hole on the other side, which leaves a negative ion on this side, which effectively develops a positive potential, and that voltage is actually referred as, that region is referred as depletion, but the voltage is referred as barrier potential. So the barrier is the distance between the p-type and n-type. Remember, the potential is the term that is used in voltage. Again, for silicon, how much that would be? 0.7 for silicon based semiconductors. Again, this is just theoretical assumption that we use. Practically, it will be somewhere around 0.5 to 0.7, depending upon what temperature that you are at. So everybody in the classroom will measure something different. For example, if you are under the vent, if the vent was on, the device was a little bit cooler, then you will read less. So the more heat, you will read more. The more heat you apply, it will conduct way earlier. So for germanium-based diodes or germanium-based semiconductors, it will be 0.3. It is possible. We need to look at the data sheet, but there is, for the safe operation, this is what the safe operation is. It's always going to be like that. And if you apply a specific temperature, there may be a possibility that it will be 0 volts altogether, but may defeat the purpose of semiconductors altogether. Because if you are operating a device at that condition, let's say you find a temperature that you don't need this 0.7 volts, then it's a conductor. Altogether, it acts as a conductor. So why do we need a semiconductor? Or you could use it as a piece of wire. Correct? Because remember that the purpose of semiconductor is to make it as a conductor whenever it's needed, to make it as an insulator whenever it's needed. Right? But if you have no barrier at all, then it's just a piece of wire. It acts like a piece of wire to allow the current flow throughout. Again, the application wise, you will see as a semiconductor soon enough. But if you say, if I don't require this 0.7 or 0.3 volts, that's a condition actually helps us to do some things, some applications. But there is a possibility at some temperature, you can make it 0 volts. That's a perfect condition, but that in real applications, it won't happen. So usually that 0.7 is like under room temperature around 70 degrees Fahrenheit. That's what you will see it. The voltage developed across the p-n junction is a barrier potential from p to the n. That's when the voltage that you are testing. So for example, the difference between these two together, because remember voltage is tested across, right? From one to another. So if you're testing between the voltage between here to here, you will read that 0.7 volts. You're actually reading across the barrier. So it's because obviously when you have a device that is already integrated, you're not going to break down to the barrier. You're not going to see visually the barrier inside. Yeah. If you have two p-n junctions together, you would have a barrier of 1.7 volts. Each one will accumulate for 0.7. That being said, one PN junction will automatically give you what? 0.7 without application of any external voltage. That means you can use a diode as a source too. If you put like 20 diodes in series, you can get 20 times 0.7. That's what solar cells are. You will get that 0.7 or 0.3 volts, depends on the solar cell or the light energy, but all those are placed in either series or in parallel to accumulate the voltage or current. Remember, if you put them in series, more voltage, right? Put them in parallel, more current. That's given when you're dealing with silicon. Germanium is lower, as you see, it's only 0.3. Because remember that for germanium, the valence electrons are farther away from the nucleus. That's why the barrier potential was lower for germanium. So if you simply holding the PN junction, this 0.7 barrier potential will actually decreases because you're applying more heat energy that makes further conduction. So that's the depletion region versus the barrier potential. So depletion region shows that the region was depleted of the charge carriers. So that region does not have anything in layman terms. Barrier potential is the voltage. Potential means it's a voltage that is being developed across the barrier once you have the depletion region. And that will account for approximately 0.7 volts. And from the energy band diagram too, it shows here. You see initially, the moment you put them together, you see the barrier is very thin. So this is an N region. That's why you see lots of free electrons available in the conduction band. Remember that conduction band is free electrons. And very few holes. But for P region, you have majority carriers which are holes right here, minority carriers which are electrons right here.
So what makes this good is if it has more than 7 volts, it makes a circuit. If it doesn't have more than 7 volts, it won't complete the circuit.
That is correct. Ideally. But there may be a different way to put it together. Because that 0.7 is under perfect conditions. Everything is good. Everything PN junction is good. But how much current actually flows, that's another thing. Okay, let's say if you don't have a 0.7, what will happen? Is there any current at all? Of course there will be current. Is it enough? Probably not. That's the two different things. So we cannot say, if I don't have a 0.7, obviously the junction will not behave as it's supposed to. It's always behave. It will always allow the current. But how much current it is allowing, that's the question. Is it good enough? That's the question.
So is there more than, there's probably a better way to make it 0.6, 0.5 to change that barrier potential, right? If you run them in series, it goes 0.5, it gets one circuit, 0.6.
It's gonna be another. Yeah, there are some applications where you place them in series. There are some applications that you can put 2 diodes, 3 diodes back to back to achieve something else. As I said before, PN junction is nothing but a diode. So remember, our first device for this course is a diode. A diode internally is nothing but it's a PN junction. So if you combine p-type and n-type, you practically putting a diode. So as you can see from this figure is, as the time goes on, and usually it happens in almost in microseconds, as soon as you put them, these carriers will move. So you see there is a distance of separation. And P region was little bit higher. You can see the energy band is little bit higher with respect to the N region. So it's basically forming a battery of, again assuming it's a silicon. So the P side is a little bit higher than the N side. So polarity is also matters. That's why the P region is supposed to be, because it's a very rich in the holes, that's a positive side of it. N is a very rich in electrons, that would be the negative side of it. So that's what happened at p-n junction, at the instance of p-n junction, but after few microseconds of junction formation. So it may not be instantaneous, but all the diodes you will use in the lab, they're already at room temperature, they're already in the lab. So when you test it, you're probably going to see 0.6, 0.65, 0.5, somewhere in the range of 0.5 to 0.7. It's always going to be available on there. So again, that's the same statement right here that re-emphasizes that if it is a silicon based, again, that 0.7 volts will be across the junction already. So this is basically the chapter 1 on basics of what is the semiconductor in terms of semiconductors, p-type, n-type material. So let me give you one more way of looking at this junction formation. Again, this is the after instance. Let's say, for example, the p-n junction is already formed. So I have all these are positively charged. Again, there may be some negatively charged. Remember that there are always minority in there, correct? So remember that when this is a p-type, it's not purely positive, correct? That would be perfect. But there are always going to be some negatively charged particles will be available, but the amount will be less. So on the n-type, you have completely, again, this is after the instance of the junction formation. You already have a depletion region. So in here, we have some positively charged particles happening somewhere here. So this is the depletion region. Again, the reason why it is called depletion, depleted means there is no net charge is available in between. So when the electron left, probably that side is completely positive all the way through, completely negative all the way through. Again, you may have, again, the number of positive, number of negatives doesn't matter. They're not.
One of those individually is filled in, each hole is satisfied.
Yeah. So you have a separation. They're not. So here you have an excess of electrons. So that side would be positive. This side would be negative. Again, if I want further more transfer across the depletion region, this voltage should be, if silicon based, then this one should be at least 0.7 volts. Can I move at 0.6? Maybe extremely small amount of current. Can I move it at 0.5? Yes. Can I move it at 0.1? Yes. But the question is how much is the current is good enough to even use it, right? So the junction is being said, there is a term we use it, it will be coming in chapter 2. This connection, the way we are connecting right now, where P side is getting positive, correct? You see here, the P side is getting positive, correct? Remember, the longer lead is the positive, the shorter one is the negative. So P side is getting the positive. This type of connection to the p-n junction is called as forward bias condition. If you flip it, that would be the reverse bias condition. So that means negative on this side, positive on this side, connected to the same p-n junction. Then this condition is actually referred as, so if you have something like that, again, of course, not at the same time, then you can say it's a reverse bias condition. And these are two different ways of using a p-n junction. Again, we will discuss what will happen individually under these conditions. But whenever you see the term bias, and you will see this quite frequently, whenever you see the term biasing or bias, that means application of DC voltage to make a device work properly. Again, biasing only implying application of the DC voltage to make a device work properly is called as biasing, or the term bias. You can also say biasing. So it's a bias, or biasing is a term used whenever you apply DC voltage to a device to make it work. For example, if I have a resistor, does resistor has any barrier potential? A resistor. Does a resistor has any barrier potential? Again, you're talking about a current. I'm talking about a barrier.
Doesn't matter how many volts go through.
So resistor is always, it's only one type of material, correct? It's not a p-type or an n-type material. It's a completely carbon composition. Resistors are. It's just a purely one type, correct? Of course, their purpose is to lower the current, right? That's the purpose of the resistors. But do we use a term biasing for resistor? Putting in other words, does resistors have any minimum voltage requirement to make them to operate, or to make them to operate their behavior? Does a resistor work at 0.1 volt? Right? So as long as you have voltage, resistor is a resistor. It doesn't matter. But for a p-n junction, you need to exceed the barrier to have a decent current flow, correct? So now can you compare with resistors, capacitors, inductors? Those doesn't require, or they don't have any minimum voltage requirement. If you apply 1 volt, they work. If you apply 0.5 volts, they work. As long as you have some voltage, they behave what they're supposed to behave. But semiconductors always have some requirement. Okay, you need to provide at least this much in order to have appreciable amount of current. Does that make sense? Such as in this case, p-n junction requires at least 0.7 to have good current flow.
What about when you're doing it in reverse bias?
If it is in the reverse bias, then there are not going to be any current flow except what we call as a leakage current. So again, this comes under chapter 2. Reverse bias means, perfectly speaking, the current is 0 amps. The junction will not allow the current when it is under reverse bias. Again, why that happens, we will see it. Under forward bias, only the junction will allow the current. We will see that as well. But the key is, One PN junction behaving as conductor, when you use it as forward bias, PN junction is acting as a conductor, which is allowing the current. But when you reverse bias the same exact PN junction, it's an insulator. You see that one device, if you use it one way, it is acting as a conductor. But the same exact device, if you change the polarity of the source, it is preventing the current flow. That's what semiconductors are. They can be act as a conductor under certain circumstances. The same device can act as an insulator if you flip the voltage. So are we clear on what is the PN junction is? Barrier voltage or barrier potential. Remember, potential is the term used for voltage, and also the formation of depletion region. So we will conclude the chapter 1. So we will take a quick break. We will start chapter 2 a little bit. I think we still have enough time and enough energy. All right, so we will take a quick break, 10 minutes, and we will start chapter 2. This is where we go getting into is the diodes. Chapter 2 is completely about the diodes. So we will take a quick break and then we will take a look at on forward and reverse bias.